But yeah, we want to get the stationary distribution through simulation. And since we're trying to go forever out to infinity, then I would think we don't care about these lengths of time. So why don't we just kind of discretize time and call this time 1 and this time 2 and this time 3, and just look at the process where it changes. So that may not have the same stationary distribution, and I want to start out by looking at a couple of examples. 2 ways you might treat this system. So let's try discretizing time in 2 ways. So we're going to move to a Markov chain like xn, and I'm going to let p be the probability you go up, so the lambda over lambda plus mu. And one transition matrix you could make is, starting from 0, you definitely have to move to 1. Like there's no, you're looking at the times of transition. So what I mean here is specifically this, like the time of the jump. So I'm not trying to use pasta, which we're going to talk more about today. And that's where you look just prior to the arrivals. I'm talking about x0 is 0 in this case, x1 is 1. So we're going from 0 to 1. The next place we go is 2. And let's go down here. And the next place we go is 1. This is just called the jump chain, and jump refers to jumps up or jumps down. It's the time embedded jump chain. Yeah, let me just write something over here. If you were allowed to jump from state 1 to state 5, so not a birth and death, but that's okay, then you would have some transition rate, Q15, that would be greater than 0. And so if you were at state I, then you transition to another state. So in this case, you will never stay at the same state because you're sort of just marking it every time it changes. So you would transition to another state with rate equaling, so you could go to, I don't know, if the state space is, say, non-negative integers, you could go to state 0 or state 2 or state 3. And you would add all of the transition rates starting at I, but not allowing j to be I. So that's the rate at which you go to another state. And that is in place of what I'm saying is mu plus lambda. So it's a more general thing. And then you would go from I to j with probability qij, the rate of going there versus all the other, or the total rate of moving away from I. So that is the generalization of lambda over lambda plus mu and mu over lambda plus mu. So let me go back to this discretization of the MM1. We are always, if we're looking at the quote unquote jump chain, which is after every transition, then starting from 0, we always must go to state 1 next. And remember, this is not a rate matrix. We're in a discrete time setting, and this is actually a probability transition matrix. So you would go from 0 to 1 with probability 1, and then everything else would be 0. This is one option. That's why I'm calling this P1. From 1, you would go up to 2 with probability P, which is the birth parameter over the total rate of leaving a state. And you would go down to 0 with probability 1 minus P, right? 1 minus P is the down rate over the total rate of leaving a state. And you would never stay flat, so you would never go from 1 to 1. And the rest of the matrix would look like this. So let me just do one more row. From 2, you could go up to 3 with probability P. You can't stay where you are. You can go down to 1 with probability 1 minus P. And so you get this above and below the diagonal bit. I want to look at the distribution, the stationary distribution of this. Now, this is like beginning of the semester stuff, and see how it compares to the geometric stationary distribution for the MM1. And I also want to look at a second possibility, I don't know that I'd fit it to the right. So sorry, I'm scrolling off screen pretty fast, but it needs its own board. So in this case, I am going to go up with probability P and down with probability 1 minus P. And what I'm going to do is when I'm at 0, I'm going to create a fake move. So what I mean by that is for my second version of discretizing this, 0, 1, 2, 3. I just want to look at this one as well. So go up with probability P and go down with probability 1 minus P, but from 0, you can't go down. So let's consider what would happen if we stayed flat there, kind of absorb that move down, and then everything else the same. So from 1, we'd go up to 2 with probability P and down to 0 with probability 1 minus P. And from 2, we'd go up to 3 or down to 1, and everything else is 0. So this is my P2 matrix. Okay, so the stationary distribution for the P1 chain, the chain running that way, I'm just going to run down the columns. So pi 0 is going to be 1 minus P times pi 1. And pi 1 is going to be 1 pi 0 plus 1 minus P pi 2, etc. So again, these were back to probabilities, not continuous rates. So let me write those down. Pi 0 is 1 minus P pi 1, and pi 1 was pi 0 plus 1 minus P pi 2. And if you had the matrix in front of you, it would be really easy to see going down the second column that pi 2 is P pi 1 plus 1 minus P pi 3, and then that pattern stays. So we get pi n is P pi n minus 1 plus 1 minus P pi n plus 1, and that holds for n equals 2, 3, and 4, because it's really kind of right there where the pattern starts. Okay, so I'm going to do this kind of quickly because it's just the algebra. I don't think you really need to see all of this. But from this first equation, I see that pi 1 is 1 over 1 minus P pi 0. And I could solve for pi 2 by plugging in this new expression for pi 1 and then solving for pi 2. So pi 2 is going to be 1 over 1 minus P. Now that 1 minus P is this one that's divided over at the end. And then I'm going to have pi 1, which is written right above, minus pi 0. So I could write this as 1 over 1 minus P minus 1 times pi 0. Why did I do that? I'm trying to get to a pattern. And if you add the fractions and multiply things out, this should be P over 1 minus P squared times pi 0. And so if you keep going, back solving and sticking the pi 0s into everything, pi 3 is going to be P squared over 1 minus P cubed pi 0. And in general, pi n is P to the n minus 1 over 1 minus P to the n pi 0. And if you look back at what we've written here, that even holds when n is 1. Yeah, we get P to the 0, 1. Yeah, so this holds for n equals 1, 2, 3 on up. It doesn't hold for n equals 0 because you'll get pi 0 on the left and you'll get a P to the minus 1 in front of pi 0 on the right. But this is enough to find the pi 0 because everything's defined in terms of pi 0. So we would sum all the pi's. And pi 0 is alone, it's its own thing. And then the sum as n goes from 1 to infinity of P n minus 1 over 1 minus P to the n pi 0. And you could take the pi 0 out And what's left is sort of looking like a geometric sum. Because the index starts with 1, I want the exponents to start at 0. So I want them to be n minus 1, which means I'm going to pull out a single one of the 1 minus p's. So 1 over 1 minus p. And then this is going to be the sum as n goes from 1 to infinity of p over 1 minus p to the n minus 1. So a nice geometric looking sum. Is this going to converge? We need that p over 1 minus p to be less than 1. But if you check out, like we have definitions here, this p is lambda over lambda plus mu, and 1 minus p is mu over lambda plus mu. So this stuff cancels and leaves lambda over mu. And this is less than 1 by the assumption that we have a stable system that we want to find a stationary distribution for. So with that, we can do this geometric sum. And after some simplification, just combining all these, I got 2 minus 2p over 1 minus 2p. And then whole thing was equal to 1. So this is telling me that pi naught is 1 minus 2p over 2 minus 2p. And as a quick sanity check, the denominator is a larger thing because it's the numerator plus another 1. So this is a number between 0 and 1. And this means that pi n is going to be p to the n minus 1 over 1 minus p, 1 minus 2p over 2 minus 2p. So this was the very natural discretization. It says you go up with probability lambda over lambda plus mu and down with the rest of the probability. And if you're starting at 0, you must go up 1 with probability 1. Remember, the second matrix I made had that sort of fake reflective absorbing state where you kind of try to go down when you're at 0, but going down means staying where you are. And this is unfortunately not equal. So if I work this out, did I do this? If I put the lambdas and mu's in here, the pi 0 is 1 minus 2p over 2 minus 2p. And if I put in the fact that p is lambda over lambda plus mu, I get mu minus lambda over 2 mu, or 1/2 1 minus lambda over mu. And so here's the pi 0 we want, but we have this extra thing. So this is the pi 0 for the continuous time Markov chain. So it's not quite right, but it's not that bad. So this is a 0 for the continuous time Markov chain, but they're not the same. So discretizing using the jump chain, every time you make a change, recording where you went, is not quite right. But it doesn't mean we can't use it, because up next, we're going to show how to relate the stationary distribution from the jump chain to the original continuous time process. By the way, I won't take you through it, but the other model actually works. So the stationary distribution for model 2, so that's where we had that fake like go from 0 to 0 with probability mu over lambda plus mu. You could go through all the same steps, and this turns out to be correct, meaning it actually preserves the continuous time process stationary distribution. So that's great, but we're not going to know that going into it. And so we will know, we already talked about pasta a little bit, I want to talk about more today, that there's certain places we can do the embedding where we will preserve the stationary distribution. And we just saw an example of those places where we cannot do the embedding and preserve the stationary distribution. But this one was kind of a guess, like, why did I make state 0 kind of reflective / absorbing? Let's talk about the jump chain and its stationary distribution and how it relates to the original continuous time stationary distribution. So this is an example of a time embedded chain. And this is the particular case where we're going to look at the process every time it transitions. So this is like P1, that first matrix. So I have a continuous time Markov chain on a discrete state space S. And I just want to say it again. It's important that jumps are up or down, because it's easy to just think jumps are taking you up. Okay, so we have a continuous time Markov chain and we have transition rates, presumably Qij. So given that you're at state I, the rate of transition to state J is given by Qij. What we're talking about right here is not restricted to the MM1 or a birth and death process, just any continuous time chain where you know the generator matrix and those transition rates. So we're going to look at the embedded chain where we define xn. This is going to be defined to be the original process at tn plus, I guess, where Tn is the time of the nth transition of the continuous time chain. So the continuous time, get a color up here, it's going to be this x of t. And this is the nth transition of x of t. This is model 1 in the example today. So this is discrete and it has its own transition probabilities. And note that we can never stay flat because by definition, we are defining the points of the chain by looking at the continuous time process every time it makes a change. So it goes from 1 to 2 or 1 to 0. So note that xn plus 1 is never equal to xn, i.e. PII, the probability you go from I to I in one step is always going to be 0 for all I in S. Okay, so I want to assume that both have a stationary distribution and then look at them and how they would relate. And we're going to get a pretty nice, neat little formula. So assume both, meaning the continuous process and the discretized process, have a stationary distribution. So I'm going to use pi to denote the stationary distribution for the original continuous time process. And then I'm going to let pi tilde be the stationary distribution for the chain we just defined by discretizing time of the discrete time so-called jump chain. So what we're going to do again is we're going to relate the two pi's, or hopefully. And to do this, we're going to note that the transition rates across any row of the generator matrix, they have to sum to 0. So note that we have the sum over j of Qij is going to be 0. And this means that something we've seen all along, the rate on the diagonal, the ith row and ith column, is the negative of the sum over all j not equal to I of Qij. And so this brings us back to the question I was answering before that was never asked, but we're at a state I, and this is the rate of transition away from state I. And we break that rate. I was going to write this in more detail, but I kind of already did it. So I guess I'll use that. The next transition has to be exponential, and it's going to be at the minimum of a bunch of exponential times. So the next transition, so assume you're at some I, is at the minimum of a bunch of exponential times, which is again exponential, and the rate is the sum of the rates. And in this case, it's going to be exponential with rate QII. So the next transition is after an exponential rate equals the negative of QII. Yeah, the negative of QII. That's going to be positive. I think I should give this a letter because it looks like a negative rate. I am going to define VI to be the sum over all J, not equal to I, of the transition rate QIJ, which is going to be the same thing as negative QII. So now this is exponential with rate VI. I don't want to use a lambda because it could be confused with other lambdas. Okay, so again, this is the exponential rate until the next transition. And so remember actually, we don't have to remember. Well, the probabilities, if you're at I, the probability would move to J in the time discretized chain would be the rate of transitioning from I to J over the total rate of transitioning anywhere. Oops. Maybe I don't really want to use QIJ in the bottom, but maybe this is easier to write as QIJ over VI. So that's the transition probability. That's in place of lambda over lambda plus mu. We have a lot of places we could potentially go, not just up or down. So there's a lot of things in the denominator. Okay, let's look at pi q equals 0. To get the stationary distribution for the continuous time chain, we usually look at this equation, and I'm going to write out, as usual, the ith element and set that equal to 0. I guess I want to make it look like our old stationary equation. So I'm going to take the sum over I of pi I qij. So that's actually the jth element of the vector matrix. And this is equal to the sum. I want to break this up. The sum over all I not equal to j of pi I qij plus pi j qjj. I just pulled one term out. Otherwise, I did nothing. But this qjj is the negative of vj, given that I defined vi to be the negative of qii. Okay, so this whole thing is equal to 0, and this implies that moving this to the left-hand side here, I get that pi j qjj is equal to the sum over all I not equal to j of pi I qij. And what I'm moving towards is, I should use I guess it doesn't matter, but I'm wondering if I should use my V notation over there. I want to do that. Sorry about that. Same thing. So Vj. What I was about to say is this is kind of starting to look like a stationary equation, kind of, sort of. But instead of having, I'm looking for pi j equals the sum over I of pi I pij for the discrete process. And because I'm using a pi tilde for the discrete process, that's kind of what I'm looking for. And so the idea is going to be like to call this maybe pi j tilde. Because what can I say about the qij? I wrote up here that qij over vi is pij. I want to plug that in. Okay, so pi j vj is the sum I not equal to j of pi I, and then vi pij. There are the transition probabilities, and that's looking a lot more like the stationary equation, but the stationary equation doesn't have a missing term. But it's okay, because I can throw in the final term. I can sum over all I, pi I, vi, pij, and the reason I can do that is because pii is 0. So if I throw it in, it's not going to hurt. And now you could kind of see, if you like lump this stuff together, it appears that starting with the pij's, a solution to the stationary equation is given by, so it appears that pi j tilde, the solution to the stationary equation, which is supposed to be the stationary distribution for the discretized chain, appears to be, but this is wrong, pi j vj. Like imagine replacing those things in the yellow parentheses with this, then you actually have this stationary equation. But the reason it's not exactly that is because if you just go multiplying your stationary probabilities by rates, you may not have a probability distribution. So I really need to say not equals, but is proportional to. Something that can be renormalized, so we'll sum it all up and divide by that. So is proportional to, because it's okay, you can throw, a 7 on both sides of this. So you can multiply or divide by something. And you would normalize this into a probability by saying that, I'm going to write pi I. Pi I tilde is pi I vi over the sum over all j of pi j vj. So there is the stationary distribution. Here's the pi I tilde, and the pi's on the right side are the original pi's from the continuous time process. And again, just as a reminder, vi is the negative of qii. That's pretty cool. Usually people don't think about that denominator. They just sort of think about this because it becomes like all other problems we do in here. You have to make sure things sum to 1. So often people write like pi I tilde is proportional to pi I vi, or pi I is proportional to pi I tilde 1 over vi. So let's try it. I'm going to go back to P1, model 1. That was the jump chain. That was the jump chain, and we found the stationary distribution, and it did not match the original distribution for the MM1. It was just a little bit off, but it didn't match. And so those probabilities that we found are these pi I tildes, and we can relate them to the pi's from the geometric distribution for the MM1 using these rates. So let's go to the example of the MM1. Let's assume that lambda is less than mu, and let's discretize at jumps. And this means you get the P1 chain. where the first row was moving from 0, you can only go to 1 with probability 1, and all the rest of them. Okay, so the stationary distribution, or the discretized process, we're going to call that pi I tilde. And it's proportional, we just learned, to the original pi I VI, where VI is the negative of QII. And the original pi I is just the geometric, it's the stationary distribution for the continuous process. So it looks like 1 minus lambda over mu to the I for I equals 0, 1, 2 on up. And then the Q matrix for the continuous time process says that we're going to move from 0 to 1 with rate lambda, and then we're going to stay where we are with the rest of the rate. But for all the other rows, for say 1, we're going to move to 2 with rate lambda, to 0 with rate mu, and all the other rates are negative lambda plus mu. So it becomes this tri-diagonal thing after the first row. And so let's try to use that up here. So our V0 is the negative of the negative lambda, which is lambda. And so the discretized chain has a distribution that is proportional to lambda times the pi I from this geometric. I guess I'll write that down. Lambda 1 minus lambda over mu. But that's not necessarily a probability. Lambda is a rate parameter and can be quite large. So this can be greater than 1 for sure. So in the end, we have to normalize these. So let me write, the rest of them are all going to follow the same pattern. So for, oh, sorry, this should be pi 0. But now I'm going to write for I equals 1, 2 on up, then the discretized chain stationary distribution is proportional to lambda plus mu times the stationary distribution for the continuous time process. So this is lambda plus mu, and this is 1 minus lambda over mu I. And I still don't know the pi's until I add them up.
Boo, you suck.
Yeah, this should be pi 0, which I did write, but yeah, that's incorrect above. Thank you. I'm so used to those recursions. Yeah, so here I have almost an explicit expression for pi 0 tilde. Like these, all of these are not in terms of pi 0 tilde, but I still need to add them to find the normalizing constant. So we need the sum as n or I, and I don't know, n goes from 0 to infinity of the pi n to be 1. And so this is 1 minus lambda over 1 minus lambda over mu plus the sum. What did I write? 1 minus. This is 1 equals. So there's my pi 0. And then n going from 1 to infinity. Lambda, let me pull out the stuff in front of the sum. So I'm just writing this down, but I can pull out the lambda plus mu and the 1 minus lambda over mu. And I get the sum as n goes from 1 to infinity, the lambda over mu to the I, and lambda is less than mu. So this is lambda 1 minus lambda over mu plus lambda plus mu, 1 minus lambda over mu, and then this geometric sum is 1 over 1 minus lambda over mu. 2 lambda. I'm going to cancel this. And I get, oh yeah, my geometric sum started from 1, but my exponent was not like a n minus 1. In fact, I don't even have an n there. This is an nth power. And I don't get the geometric distribution until I get the the first exponent to be 0. So I'm going to pull out a single lambda over mu. That will make this lambda over mu to the n minus 1. And now I can get my geometric result. And now I can cancel this and this. And let's see, I'm just going to have to multiply lambda minus lambda squared over mu plus lambda squared over mu plus lambda. So we get 2 lambda. That is the normalizing constant. And so we now know, since our discretized pi 0 looked like this, if I divide by 2 lambda, if I divide every single pi by 2 lambda, then they'll sum to 1. So in conclusion, pi 0 tilde is lambda 1 minus lambda over mu over 2 lambda, and the pi n tilde is lambda plus mu 1 minus lambda over mu to the n. Oops, that's 1. 1, 2 on up. And check this out. Those lambdas cancel, and this is 1/2 1 minus lambda over mu, which is what we saw when we went the long way to find the stationary distribution of the jump chain. So if we usually you would use this in the other direction, like you would not know the stationary distribution of the continuous time process. So you would go the long way using the probability transition matrix and the stationary equations, and you would find these outright, and then you would relate them back to, you would get the continuous time probabilities using this relationship. So usually you end up going the other way. But we did it. We got what we actually observed when we time discretized the chain at jumps. So it matches. All right, so the usual use of this is simulation, or, in some cases, the stationary distribution, because this is for any continuous time process. So it doesn't have to be birth and death. It doesn't have to be up and down by 1. It doesn't have to be a queuing model. So if you can't solve pi q equals 0, maybe you can discretize it and solve for the stationary distribution pi times p equals pi. And since you can relate them, you can get from one to the other. So if one of them is easier to solve, you can get the exact solution for the other. But also, if you wanted to simulate the continuous time process and you decided to just say time 1, time 2, time 3, I'm going to have a jump up. I'm going to go up or down with probability p or 1 minus p. Then you could take your results, the distribution you find out here, and adjust it to get the distribution of the original continuous time chain where you actually put the exponential times in there. That's pretty cool. Okay. So let me write down pasta. Talked about it a few times. It stands for Poisson arrivals, C time averages. And so this says that for anything, like any sort of Markov system, fed by an external Poisson process only and not other input. So fed by an external Poisson process. So that means we've got a process with some rate lambda coming in, and then things happen. If it's queuing, we might have a whole bunch of different stations, and people may be routing around and doing all sorts of things. But we've got some kind of Markov process that is being fed by an external Poisson process with rate lambda. Embedding time not the way we just did it, but just prior to arrivals or just after departures. This is a way to discretize time. We'll give a discrete time Markov chain xn with the same stationary distribution. This is something that's often used in simulation as well as, you want to discretize time. And this is, I don't know if it's easier or not than using the jump chain, but it's another form of embedding. I'm going to give you a tiny sketch of a proof, but let me do the pictures first. So if this is like an MM1 and we have 0 people, and then we go along and we get 1 person, and we go along and we get 1 person, and then we come down, down, whatever. So the pre-jump chain is to say we're starting at 0, then we look just before the jump, Oh, I am using the words incorrectly. Jump means up or down. So the pre-arrival process is what I really mean, just before we go up. And so this would result in a Markov chain x0 equals 0, x1 equals 0, x2 equals 1, x3 equals 1, and that's all I get to see there. But if I take the same process and look just after the jumps, no, sorry, just after departure. So this is the person who is leaving the system looking back over their shoulder. So the first, let me go away. Here is the first place someone leaves this system. And they are, when they leave, when they were in the system, there were 2 people. And when they left, there's 1 person. And so after they leave, they look back and there's 1 person behind them. So this chain starts at 0. And the first time we have a departure and look back, we're at state 1. And the second time we have a departure and look back, it's going to be right here where we're at state 1, etc. So I claim both of those have the original stationary distribution, and neither of those is the same as the jump chain we've talked about for most of today. If you get anything from this, it is going to be that if you need to simulate a process to learn something about it, you do need to be careful about discretizing time, because you could mess up the very thing you're looking for. You could have a process that has a stationary distribution and then doesn't because of the way you discretized it. So this would be a chain, like maybe call it xn. This would be a chain, maybe yn. And I claim they have the same stationary distribution, or Pasta claims this. And so here is a sketch of the proof. In the module, when I put that up today, I'm going to put a paper by Ronald Wolf. If you care, you don't have to look at this in today's module. But yeah, the idea is if you look at so continuous time process, the state of the process at time t equals some j, and you decide to say the state of the system as seen by an arriving customer. Oh, I'm proving it the arrival process one, where I'm giving a sketch only in the case of the yellow chain, the pre-arrival process. So people are coming in and what they see ahead of them is supposed to be stationary. So this means that if you let n of t be the arrival process, then n of t plus delta minus n of t is 1. This is just a sketch, so I get to say things like this, or very small delta. So this is supposed to be the state of the system as seen by a customer arriving at time t. like just after, they're looking before them and that's what they see, and then they join. And there will be a limit in delta here in the real proof. And I can write this out as the intersection over the marginal probability, and then I can rewrite the numerator by turning things around. And that would be given x of t equals j times the probability x of t equals j divided by the probability of the stuff after the conditional line. So I did do two things at once here. I rewrote the numerator, unraveling the definition of conditional probability. So the assumption behind pasta, I don't think I was clear about this, but it's not just that the system is fed externally by a Poisson process with rate lambda. Maybe implicit in that is that that process is not being affected by what's going on in there. So there's no balking, there's no people leaving because there's too many in the system. So if the arrival process, and that's what the N is in this problem, is here's an arrival, and if it's independent of the state of the system, then, well, that's our assumption when we say the arrival process is Poisson. So I get to drop this because the arrival process is assumed to be, so I should write that, I guess, is assumed to be independent of the state of the system. Okay, so once I drop that, then I've got this and this is going to go away. And so I'm left with the probability that x of t equals j. Very hand wavy, especially with that delta being small. But now, so this is the state of the system as seen by an arrival, and this is just the state of the system, period. So if you take the limit on both sides as t goes to infinity, then this should be converging to the stationary distribution of the continuous time process. And this is converging to the stationary distribution of the discrete time process just before the jumps. And they're the same. That is not the proof. That is a very thin sketch. I'll put the paper up in case you want to see it, but that's the idea. So same limit if you just run the chain, the continuous time chain, and go out to infinity, or if you run it and you only look at it given that you have an arrival coming up in the next instant of time. That is the end of time discretization. Again, the thing I really want you to take away from it is unless you discretize your process carefully in time, you may destroy properties of the original process that you're trying to, maybe look at through simulation of a simpler discrete process. So you have to be careful about when you discretize time. In some cases, you preserve the stationary distribution. In some other cases, we know how the new stationary distribution relates to the old one. Okay, so here's something fun, I think. I wanted to talk about server idle time. So when the server just is not working, idle times and busy periods. And what we're about to do can be, let's just do it again in the context of an MM1, but you can do this kind of analysis for many different queuing models. So the process started somewhere and is going. At some point, it empties out. And then at some point later, someone comes in, and maybe someone else. So if you go to maybe a time that it first empties out and look until the next time it empties out, then this is an idle period for the server, right? Because there's no one there. So the server is taking a break. And then when someone comes in, they bring in their own work for the server. And maybe during that time, other people are coming in. And so we start, that person starts a busy period for the server. So it turns out that the long run proportion of time that there's no one in the system is going to be able to be represented by the sort of proportion of idle time to kind of this whole timepiece. So I claim it's going to be the expected idle time over the expected idle time plus the expected length of a busy period. Idle length, which feels good, I think, intuitively. Busy period length. So let's check it out. The expected idle time, when the system goes empty, it's only going to stay empty until someone comes in. And the arrival process is a Poisson process with rate lambda. So we already know that the expected idle time is the expected value or mean of that exponential. So 1 over lambda. But the busy period is more difficult. And you know what we do. We start conditioning on things to make it easier. So let's look for the expected length of a busy period. And one thing I need to know, so there is at some time, someone comes in and starts the busy period. And we need to know at least, like they're going to be in there, or the busy period is going to be at least their service time. And we'll also have to consider people coming into the system. So I'm going to condition on the service time of that first person who breaks the idle period. The service time of the customer who starts a busy period. The service times in the MM1 are all exponential with rate mu. So this is going to be exponential with rate mu. And so let's condition on that to find the expected value of B. This is the integral from 0 to infinity of the expected value, the expected length of that busy period, given the service time of that first customer to break it being S times that exponential rate mu, PDF in S in this case. But I don't really know the expected length of the busy period just based on the time that that person was in the system, because it also depends on who came in while they were in service. So I'm going to condition once more. In other words, I'm going to look at this conditional expectation, and I'm going to condition on the number of people who come in when that person is in service. Let me move this down a little bit so I can say that. I'm going to let N be the number of people or customers who arrive during the service of that customer, the one that's breaking the idle period. Okay, so yeah, I'm going to compute this by conditioning on N, and no one could come in, or someone could come in. So I'm going to get the sum as N goes from 0 to infinity of the expected value of B given S equals S and N equals N times the probability that N equals N staying in that conditional universe where S equals S. Okay. We know this distribution, given a length of a time interval is S, the number of arrivals during that interval has a Poisson distribution with rate lambda times S. So the probability that we get little n arrivals, this is e to the minus lambda s to the n over n factorial. And let's work out yet another thing that I have to pull out onto its own line. So what is the expected length of a busy period given the service time of the customer that broke that idle period and no customers come in while that person's being served? This is just the service time of that customer, right? So this means someone came in and then they left and no one else came in. So the busy period is just a service time. And given the service time is some fixed little s, we're done. But the expected busy period given s equals s and n equals 1, we're going to have to wait through the service of that person. And then the next customer starts their own busy period. So we get the expected value of b. So that I'm assuming we're in equilibrium or stationary mode. So this is start of a new busy period by like the next customer. The expected length of the busy period given s equals s and n equals 2, we're going to have 2 busy periods come in, one started by the second customer and one started by the third customer. So this is s plus 2 times the expected value of b. And in general, the expected value of the busy period, given that the service time of the first person is s, and given that n people arrived during that service period, this is s plus n times the expected value of b. So we can put it all back together. We had an expected value of b on the left side of the very beginning of the first integral, and there'll be some on the right side, but we can solve for the expected value of b. So let's look at the expected busy period given s equals s. This is the sum as n goes from 0 to infinity of these expectations times the Poisson distribution. So s plus n times the expected value of b. By the way, this formula does work when n is 0, right? We just get the s plus 0b, 0 times the expected value of b. And then e to the minus lambda s over, this was n, to the n over n factorial. I think we should distribute these, distribute this across. The first sum is the expected value of that Poisson. So this is, I don't have notation for that. This is the expected value for a Poisson random variable with rate lambda s. This is bad notation. And no, sorry, it's not. I would need the n because I'm summing over n. That's actually not an expected value. Sorry about that. This s would come out of the sum, and I'm just summing up the Poissons. So this is s times 1. And the other part is the expected value of b, and then that is the expected value of a Poisson lambda s random variable. Right, I have the sum here, and I pulled out the expected value of b because that doesn't depend on n, and I'm left with n times those Poisson probabilities. Anyway, s plus the expected value of b, and the expected value of a Poisson with parameter lambda s is lambda s. That first. Okay, so that's not the original thing. The original thing was the expected value of the length of the busy period. We wrote it as the integral 0 to infinity, the expected length of the busy period given s equals s times the PDF for S, which was mu e to the minus mu S ds. And now I have something to plug in, 0 to infinity, S plus lambda S, expected value of B times mu e to the minus mu S ds. So distribute this and form two integrals. The first one is the integral from 0 to infinity of S times mu e to the minus mu S ds. That is the expected value of this exponential, and that is 1 over mu. The mean for the exponential is 1 over the rate. And the same thing's going to happen, actually. I should just pull the S all the way out. Why don't we do that? Why don't I write this as 1 plus lambda expected value of B integral 0 to infinity of S mu e to the minus mu S ds. And so we get, so this is the mean, this is 1 over mu. So we get 1 over mu, 1 plus lambda expected value of B. And this is the expected value of B. So we can solve for this. This is equal to this. And if we move things around, I'm going to get 1 minus, then we're going to get the expected value of the busy period is 1 over mu over 1 minus lambda over mu, which could simplify to 1 over mu minus lambda. That's weird. We've seen that before, as that's the mean of the part of the waiting time distribution that was not 0. Remember our mixed random variable W that was 0 with some probability and exponential with this rate with the other probability. But yeah, we do have the expected idle period over the expected idle period plus an expected busy period is 1 over lambda over 1 over lambda plus 1 over mu minus lambda. Yeah. This is 1 over 1 plus lambda over mu minus lambda. That is mu minus lambda. That is mu minus lambda mu minus lambda plus over mu. And that is 1 minus lambda over mu. And that is in fact pi 0 for the MM1. But we now have it in this kind of intuitive way about the long run proportion of there being 0 people in the system is like the proportion of an idle period to the full idle and busy period. So that feels good intuitively. So, wow. Right, yeah. So I've got a minute, but that's not enough to do anything. The very next thing we're going to do, I'll just describe a few things, is the MG1Q, and that's where we have general service times and not exponential, and it's no longer Markov, but we can do things with it. And then we're going to look at Jackson networks, which are basically stringing a lot of queues together. And we're going to look at 2 more algorithms, the Gibbs sampler, which is the other big famous MCMC algorithm after Metropolis Hastings, and perfect simulation, which is no convergence error, and then whatever else we can fit. Next time. Oh yeah. Yeah. Yeah, I'll definitely make a note to do bulking. What the heck? I'll put that here so I'll have the note. Next time on Markov processes.